we are facing a lot of energy issues, and we have been for some time. And one of the things we'll talk about in the next set of chapters is the idea of fuel cells as one potential solution to some of these issues. Now, fuel cells run on hydrogen, and the problem is hydrogen isn't easy to get. So let's take a look at some thermodynamic issues to get at hydrogen production. We're going to use these as test cases. So we want to know whether or not we can use these chemical reactions to produce hydrogen. So let's take a look at a couple of them. There's two common chemical reactions used for producing hydrogen. These are, one of them is the water-gas shift reaction, the other one's steam reformation. And these two are illustrated here. So let's just take a look at, is this reaction spontaneous? Are these reactions spontaneous? So let's just take a look. Let's just take a look at A. Is this reaction spontaneous? Well, the easiest way to figure that out is to determine the delta G of the reaction. The delta G of the reaction will equal the sum of the delta G's of the products minus the sum of the delta G's of the reactants. And so we can go to our tables and dig up the delta G's for each of these components. And so we have carbon monoxide, products, again it's always products minus reactants. Just be cautious to use the correct, this is water in the gaseous phase. And so once we have these values, we can predict whether the reaction would be spontaneous under standard state conditions. So we did measure the delta G for this reaction A, and we find that at room temperature, this reaction has a delta G of 141 kilojoules. The fact that it's positive means that it is not spontaneous. We can do a similar analysis for reaction B, though for the second reaction, the delta G of reaction is equal to negative 28.6. So of these two reactions, we could see that one of them is spontaneous and the other is not. So while it looks like it would be fairly easy to use carbon monoxide to make hydrogen, it's not necessarily easy to use straight from methane. But what if there was a way to make this reaction spontaneous? We've talked about one major way to tell if this reaction is spontaneous is to examine the temperature dependence on the spontaneity of the reaction. Is there a temp where this reaction becomes spontaneous? Is there a temperature where this reaction... Now, this type of question, what we really need to be looking at is also the delta H's, the enthalpy and the entropy component of the reaction. So we're just going to look at reaction A. We already know that reaction B is spontaneous at room temperature. It might change its spontaneity, but we don't really care about that one. We'll just take a look at this one where everything is a gas phase. How do we determine whether or not this reaction has some sort of transition point where it becomes spontaneous? For this, we turn to the definition of Gibbs free energy. Delta G is equal to delta H minus T delta S. And depending on the values of delta H and delta S, we can see if there's a transition point, a temperature at which it transitions from spontaneous or not. So for this, we need to know the delta H of the reaction and the delta S of the reaction. Again, our tables. So you should be able to calculate the enthalpy change in the reaction and the entropy change using your tables. I'll let you go to it. So for the enthalpy change, you should get a value of about 205.9 kilojoules. For the entropy change, you have to be cautious though, because unlike enthalpies, the entropy for many materials elements is non-zero. So you have to be sure to include everything. So if you do the calculation, you obtain the following, that the delta H of the reaction for reaction A would be equal to 205.9 kilojoules, and the delta S of the reaction would be 214.7 joules. From the observation of the sign of both of these, we can say that when T is large, delta G will become negative. And in fact, we can rearrange this equation such that at that transition point, delta G will equal to 0, and you get the following. Delta H divided by delta S will equal T, the temperature at which this reaction swaps from a spontaneous form to a non-spontaneous form. The only caveat is the units. We have to make sure that the units are consistent. So plugging the values down below in, we get 205.9, 959 Kelvin. It says that at about 1,000 degrees, this reaction should become spontaneous. In fact, industrially, they actually run this reaction at 110 C or 1,300 Kelvin, right, to basically run the reaction more efficiently. So we can predict when this reaction would be transitioned from a spontaneous to non-spontaneous. So that works when you have these situations where the reaction shifts from spontaneous to non-spontaneous. But what about reactions that are always non-spontaneous? Can we never make them spontaneous? I mean, if you take a look at the delta H's and the entropy and the enthalpy components of a reaction, one may be, the enthalpy component may be positive and the entropy component may be negative. Under those kinds of situations, the Gibbs free energy is non-negative at all temperatures. They are just not favored regardless of whether or not you heat them up or not. Does that mean that there's no chance that the reaction would go? The answer is no, because that is where our other major form of our free energy equation comes in. And that's when we deal with non-standard state conditions. In those situations, again, the delta G of the reaction is equal to the delta G naught of the reaction, the delta G gives free energy under standard state, plus RT ln Q, where Q is our reaction quotient. So basically we can adjust the concentrations we can use this non-standard state condition to actually predict minimum concentration or maximum concentrations that would be needed to cause a reaction to be spontaneous. So for instance, water boiling. We know that water boils spontaneously at 100 degrees C. Actually, we calculated that in a previous example using this same strategy that we employed on the previous slide. But let's take a look at it. Let's ask a different question. How can we boil water at 25 degrees C? It turns out that there's a minimum pressure required that once you reach it, it will cause water to boil spontaneously at that particular temperature. It's usually when the vapor pressure is met by the atmospheric pressures. So we can use this form of the equilibrium of the Gibbs free energy equation to relate this to non-standard states. And again, Q is products over reactants, and so in this case we could say delta G, we want the delta G to equal 0 at that particular point. That's when it transitions from a spontaneous to a non-spontaneous point. And so the delta G naught would be equal to negative RT ln Q, which is the reaction quotient, which in this case would represent the partial pressure of water in the gas phase over liquid water. And since pure gases and pure liquids and solids don't show up in our equilibrium statements, they don't show up in our reaction quotient. And so we can use this to determine the minimum pressure. So if we plug our values in, divided by 8.314 joules, and you'll have to do a little bit of massaging of this to get it into kilojoules to make it compatible with our temperature of 298 equals the natural log of the pressure of H2O in atmospheres. Says that 3.43 is equal to the natural log of the partial pressure of water, and then we can E to the negative 3.43 will equal partial pressure of H2O, which would have to be the minimum pressure that it would have to reach. Pressure would have to be 0.0323 atmospheres, or about 24 millimeters of mercury. And it turns out that you can actually get to these pressures very easily, so you can actually boil. Converse would also be true. You know how this is the whole idea of the pressure cooker. How can you drive up the temperature? At what temperature can you, if the pressure was 2 atmospheres, what temperature would the water boil at, etc., etc. So you can use the same basic strategy. We can so we can make a reaction spontaneous, go from a positive value to a negative, one of 2 ways. At the moment, we can talk about changing the temperature, and that's a special case. That only works if there are situations where it actually undergoes an inflection point, or we can alter the concentrations. That deals with the reaction quotient. Again, this is directly tied to things like Le Chatelier's principle, where we alter equilibriums. We turn them running forward to running backwards, depending just by altering the concentrations at equilibrium. So it's very much related to equilibrium ideas. Well, it turns out there's a third way to make a reaction spontaneous. And this is what we call coupled reactions. It's possible. A coupling isn't a single reaction. It actually involves multiple reactions. And so let's just take a look at an example. Zinc sulfide, solid, being used to form zinc solid. And sulfur, zinc sulfide is a commonly available mineral. You can dig it out of the ground, and if you wanted to do your mining or your forging, and you wanted to make a bunch of zinc, it might be possible to heat this zinc up and drive off the sulfur. Unfortunately, this has a positive delta G. So the delta G of this reaction under standard conditions is equal to 198.3. And it turns out that, just cooking it's not going to do anything. You're going from one solid to two, and it's an endothermic. And so it just doesn't work. It doesn't work. But you can do a second reaction at the same time, sulfur plus O2, to give us SO2 gas. This reaction, the delta G of this reaction, is negative 300.1. But as we saw with our earlier thermodynamics, we can add these two reactions together to create a new reaction. Zinc sulfide plus oxygen goes to zinc plus SO2, where the sulfurs cancel. Turns out that the delta G of this reaction is just the sum of the other two. This is Hess's law. And we can use that to measure the delta G of this reaction, and we turn it up to negative 101.8 kilojoules per mole. So we can build chemical reactions. We can take one chemical reaction and do it in the presence of another chemical reaction and drive the chemical reaction's formation. This is central to metallurgy and completely germane to biological processes, central to those biological. So what's funny about this, though, is, and not 100% is, but we don't necessarily have to do the reactions at the same location. We don't, it's kind of one of those mysteries. We can, the universe only cares if we make enough, if we have enough entropy. So it's possible to separate the chemical reactions. And this idea of separating the chemical reactions is one that is very much at the center of electrochemistry. So coupling of chemical reactions allows us to create new reactions and make a non-spontaneous reaction spontaneous. And where this really shows up is in biological systems. I won't talk about any examples at the moment.